Okay, welcome. Today we're going to be doing logarithmic functions. Our goal for today is to analyze and identify key characteristics of a logarithmic function. Why don't you have a go at the do now? I will pause the video for a second while you do these questions. Okay, welcome back. So we need to determine on this one whether it is an exponential, logarithmic, or function or neither. In order to do that, what we want to be doing is you want to look at the pattern of progression. So here we can see that we have plus 2, plus 2, plus 2.
Plus 2.
Yeah, but that's a different, sorry, I'm with you. Plus 3. This in itself doesn't mean it's not a exponential function. In itself doesn't mean that it's not. It is possible to have a data table for an exponential function and not have equal length input value intervals as long as everything works. So if we look at here, we're doing multiply by a half. This one is multiplied by a half, this one is multiplied by a half, and it's at this point here we can say that it is neither, because it would have to be a sort of different value. So each step would be multiplied by a different amount. And it would be possible to have 3 lots of that amount in order to make the step here correct. But as it's always going, the output values are increasing proportionally, the input values are not increasing additively at an equal amount over equal length input value intervals. So this one is a neither. So for an exponential function like y equals 2 to the x, what happens to the output values each time x increases by 1? So we can see this base here in this function, and we can see that they're going to be increasing, they're going to increase by factor 2. They're going to be multiplying by 2 each time we go up by 1. We can see that in the base, and this is how it's going to occur, and this is a multiplicative change. So exponent, and this is the key information from last lesson. This is the key information in 3. Exponential functions change. I'm just going to put MULT for multiplicatively in the output value. In the output values for equal additive changes in the input.
So it will be opposite around for logarithmic.
And then it would be the opposite way around for the logarithmic. So here we're going to be adding, here we're going to be multiplying. And it's key to remember that to understand this. So we're looking today at understanding a more general, big picture understanding of the logarithmic function. So a logarithmic function is going to look like this. We can see that it's a rearrangement of an exponential function. It's important for us that the base is not equal to 1. You can't have a 1 under the base. The base value should be positive. The base value should be positive. This is because if we think where the base comes from, as it's a rearrangement of an exponential function, an exponential function is y equals a to the x. So this would then rearrange into y equals log base a of x. So sorry, let me do it to b. So if y equals b to the x, then the logarithm function of the inverse function is y equals log base b of x. Now if b in the exponential function is 1, you're going to get no change. If b is negative, the function is going to bounce up and down for integer values, and for non-integer values, you're going to be trying to square root or take a root of a negative number, which is not possible, which is why b cannot be negative. So looking at the graphs of the function, a logarithmic function is going to have look like this. We have a vertical asymptote. We have a vertical asymptote in the standard one at x equals 0. The function's going to go through this key point here. What's the point where it crosses the x-axis for the base function, the parent function? We need to know this number. In the exponential function, what value of x produces a 0? Sorry, what value of x produces a 1?
0.
0. Yeah. So this is going to go through 1, 0. This is a key point to remember. It's going to go through 1, 0. This is a very important point for us in understanding these functions. I want to have a look at what's going to make it increase or decrease. So if you look at the shape of the function is a monotone function. It's a monotone function. You have that word there? The function is a monotone function. This means it's either only ever going up or only ever coming down. When it's only ever going up, like this one, on this function, or it's only ever going down. It's only ever concave up, or it's only ever concave down. There's no change in direction. Let's have a look at the values that create that. So you only have a couple of conditions that create this. So here in this function, this is a typical rising logarithmic function. The b value is bigger than 1, and the a value is bigger than 0. Yeah. No. Let's take a look at a log function. Let's have y equals 2 times b to the x.
What's the difference between GeoGebra and decimals?
It's really no difference. It's really no difference. I think.
Okay, so if we change the b value, if b is bigger than 1, sorry, I drew the exponential function.
Where you represents the function.
Yeah.
So here's the logarithmic function. If we change the value of b, as long as b is positive, it's going to always be going up. As long as b is positive, it's always going to be up, it's always going to be concave down. As long as b is bigger than 1. b can't be 0, but it can be between 0 and 1, and then we get it coming down. Let me take away the exponential. So if we increase b, it's going to be going up when it's bigger than 1. We come down to less than 1 in this little interval, and it's coming down. So we go from 0 to 1 for this shape, and we go for bigger than 1 for this shape. Unless you make a negative. So if we make a negative, we're going to be getting this shape, but then we can get the other shape if we make b between 0 and 1. This one.
So if b is negative, then this doesn't work.
Yeah, it doesn't work if b is negative. Let's see what happens there when I pull that across.
Because B can't be. Yeah,
It just disappears. So basically, a being negative creates a reflection of this, and it creates a few other possible conditions. So the function is either always concave up, always concave down, always increasing, always decreasing. The end behavior. So the end behavior is that it's going to go towards either positive infinity or negative infinity, depending whether it's concave up or concave down, increasing, decreasing. The other end behavior is it's got this vertical asymptote. So it will go to negative infinity or positive infinity as it approaches its asymptote. We can move that asymptote around. We can can move that asymptote around by putting a horizontal translation in here. So if we translate it horizontally, did it make me messy? 100%. If I move my C slider, it's going to move the vertical asymptote. We can see the vertical asymptote is going to be here, x equals C. And depending on what the value of C is, we get this vertical asymptote there. Notice this point. I said this is the important point. So we want to find this one. So notice this point here is going to be C plus 1. Remember, in our normal parent function, it's at 1, 0. And this point is going to move across like this as C plus 1. So that's the general idea of what this function is looking like. Let's have a go. I think these questions are easier. So just take a minute now and have a go at these questions. I'll pause the video. If these so if b is greater than 1, it's going up. If b is between 0 and 1, it's doing that. Okay. Greater than 1, less between 0 and 1.
Well, isn't that how it is with A being greater than 0 and less than 0?
As well. So there's two ways to create
So
that.
what if A is greater than 0 but B is less than 1? Which one wins over the other?
So it just reflects it. So this one would be, let's say we have A as being positive. This would mean that B is greater than 1.
So if we know that A is positive, then B is greater than 1.
If A is negative, B would be. So either of these two conditions would be that one. And then this is where A is positive, B is between 0 and 1. It would look like this. Or you can just reflect that one, where A is negative, B is greater than 1.
It can be either or.
All right, let's have a look at our answers. So what is so we've got a graph drawn here. We have the limit as, we have the right-hand limit as we approach 0. This is going to go towards negative infinity. And then as x increases without bound, f of x is going to increase without bound. Here in the second one, we have our limit as x approaches 0 from the right-hand side of f of x. This is going to go towards infinity. And then we would have our limit as x goes towards infinity of f of x is equal to, and it will just keep going down towards negative infinity. So here for the third one, which one is this one going to be? This graph has the b value being greater than 1 and the a value being positive. So this is going to be like the first question. This is going to be a graph that looks like the first question. Okay, so some similar questions now. Have a go at these questions. I'll pause the video for a second, maybe. Mostly have a focus on question C. Alright, these ones are pretty easy. The first one, is it concave up or concave down?
Down.
Concave up.
It's concave up.
No. Other way around.
Concave up. Is it increasing or decreasing?
Decreasing.
Decreasing. The second one, is it concave up or concave down?
Concave down.
Concave down. Is it increasing or decreasing?
Increasing.
So for the third one, what I recommend you do is you sketch it. So this one, we have our b value, which is greater than 1, so that's like that. But then when we reflect it, it's going to be this one. We've got a reflection caused by the a value being negative, so it's going to be a graph looking like this one. So then, is it concave up or concave down?
Concave up.
Concave up.
Concave up, increasing or decreasing?
Decreasing.
This is the tricky part. So we've got selected values of the function, logarithmic function shown in the table. We have to find the value of k. So it's important that it tells us that these are logarithmic functions. So what does that tell us about the input values?
They're all additive or multiplicative.
Which one?
Or they're all either additive or multiplicative.
Output is multiplicative.
No.
No.
Logarithmic.
The input is more.
It says here, logarithmic functions. What do we know about the input values? This is the key piece of information. It's multiplicative increases. So the values are going to be increasing multiplicatively, while the output values increase additively over equal length output value. So we can see here it's going up by +1 all the way through. So we have to find what number this is multiplying by.
2.
This is multiplying by 2. So as we go up +1 in all of these, we can see that the output value intervals are equal. So the multiplicative values are going to be equal. So we're going to doing a multiply by 2 here. So k is equal to 4. Side question. What function is this? So, when we're trying, exactly what functions? We can work out, we're going to get questions, so we have to work out what the function is. So, start with your base. This number here, that's your base. So we can see that we've got something which is log of the base 2. Log of the base 2. What's the key point it has to normally go through? So if it's log of the base 2, it's going to be going up like this. What's this point normally?
0.
This is 1,
Is equal to 0.
1 comma 0. So when the input is 1, the output it should be 0. When the input is 1, the output is not 1. So this is log base 2 of x plus 1. By adding 1. Another interesting point to help us with our analysis is this point here. Now this point here is the point b, comma 1. The output of the function is going to be 1 when we insert the base. So in this function, when we insert 2, 1 will come out. But if the base was different, different values come out. You can sometimes use this point as well to help in your analysis. So our second one, we can see that we're going up by 5 every time. Always going up by 5. So what are we multiplying by here and here?
3.
3.
This is multiplying by 3. So what did we multiply here? We multiplied by 3. So k is equal to 2.
Oh, yeah, 2. Sorry. I was checking.
What would the functions look like a little bit?
Y equal log base 3.
We can definitely see this bit. Y equals log base 3 of something.
2.
Why can we see this? Why can we see that it's this?
Because it's
multiplied by
increased.
factor of 3.
We can see we're multiplying by a factor of 3. Okay. So we don't have a verdict. So this 0 here, that would mean, that should be that we're putting in a 1 here. But we're not.
X minus 1.
We're putting in a 2. K is equal to 2.
Yeah.
So what can we put inside the bracket here? So that when we put in a 2, it turns it into a 1 before we value it.
Wow, over 2.
So if we divide this by 2, if we divide this by 2, when you put in 2, you'll get 1. So you'll get 1 comma 0. Now, so when we put in our next value, see the best way to do it? When we put in our next value, it would be 6. That would be a 3 inside here. And remember this point here, b comma 1, this point here. So when we put in 3, we should be getting a 1 out. Why are we getting a 5? If there was plus 5, we wouldn't be going through there. This one has to be multiplied by 5. We've got our 0 in the right place, so we don't have a vertical translation. So in that case, if we multiply by 5, we'll get this value. All right, for this one here, we are multiplying by what value?
Upward.
It doesn't go up at a constant rate.
Yeah. So how do we find the value of k on this one?
1.
It goes from 1 to, and then goes from 7 to 19.
It's 5 times 5 over 4. Yeah, 2 multiplied by 2 minus 2.
Just gonna clean up my screen a little bit.
So isn't it 5 over 4?
We could try 5 over 4, but that's not going to work for the next one. Yeah, let's see how we can find the translation. So what type, we can see we've got an additive increase of 1, 2, and then we might assume that this would be 3, 4. It's not quite going to work, no? So we're looking for a pattern here on this one. We're looking for some number that we can subtract, and then we'll get a multiplicative one. So with this type of a question, they're never going to be making it too tricky for you. It's never going to be unlimited powers. You're working without a calculator on this one. You're going to be either getting the powers of 2, which are 1, 2, 4, 8, 16. These are the powers of 2. You might get the powers of 3, 1, 3, 9, 27, 81. You might get the powers of 10. That's an easier one. 1, 10, 100, 1,000. Possibly the powers of 5. 1, 5, 25, 125. So we can clearly see that the progression here is not enough for the powers of 5 or 10. It's just not going up quick enough. We can't take an amount off. So we're going to try and take an amount off these until we get one of these two patterns. Notice that we have, if we have +1 here, watch this. This is a +1, this is a +2, this is a +4, this is a +8. Because 7 plus 12 will take us to 19. 7 plus 12 will take us to 19. This double jump is 4 plus 8. Can you see that?
Yeah.
That's this pattern. That's this pattern. So let's make it fit this pattern. So what do we have to take off to make it fit that pattern?
-3.
-3.
Oh.
So we want x minus 3. That will give us 1, 2, 4, and 16. So in our progression, this should be 8. So what is k?
8.
11.
Oh.
11.
Oh.
K equals 11.
I know it. Just
So obviously this is going to, I'm not going to find the functions, it's not asking us to, but I think it's useful for us. We would have something on the lines of log base 2, because it's powers of 2, and in here we've got an x minus 3. Not going to dig into that much. All right, so here on this one, what are we multiplying by? What we can see is, look at the exponents. There's a 1 here on this one. The exponents are increasing additively by +3, but that means we're multiplying by e to the 3. If we multiply by e to the 3, then the exponents will have an additive progression of +3. So in our last one, what is k going to be equal to?
E to the 4.
E to the 4. Okay, our last question. The domain and range of the following functions. What are the domain and range? Take a couple of minutes and actually have a go with these ones. I will pause the video here. Alright, so for these functions, this function here, we don't have any horizontal translation. I'll just do a quick sketch. This function is going to look like this. It's going to go through 1, 0. It's going to go through 3, 1. This function looks like this. Our vertical asymptote is going to be x equals 0. So this is x is greater than 0. And this is x is all real numbers. Our second one, we have a horizontal translation. So is it going to move the vertical asymptote to the right or to the left?
right.
To the right.
It's going to move it to the right. We're going to go to here. This is the line x equals 3. Is the function going to increase or decrease? It's going to decrease. It's going to look like this. It's going to decrease because we have a negative here, and our base is 2. So it's going to cross the x-axis here at this point. What is this point?
0. 4 and 0.
This is 4, 0. We have another point here where the y value is -1. Discuss with the person next to you what the x value is at this point.
6.
Oh, sorry, not -1.
-5.
-5.
5. 6. And you just.
And it's your line. Oh, no.
Because if you put 5, it's 2.
What is the x coordinate at this point?
5.
This x coordinate is going to be 5. Look what happens when we put it in here. We've got minus 5 log base 2, and we're going to put in a 5, like this. So this gives us minus 5 log base 2 of 2. Now this gives us minus 5 times 1. This is why this point is important. So when we put in the base into the thing, we get a 1 out, and we multiply by negative 5, we're going to go through this point. So the domain for this function is going to be x is greater than 3, and the range is all x. Sorry, all y. So our last function, are we going to move the vertical asymptote left or right? Why? Because it's a positive here, so we're moving the vertical asymptote left. What is the equation for the vertical asymptote going to be?
Negative 3 over 2.
X equals? Don't forget to always say x equals negative 3 over 2. Is the curve going to be concave up or concave down? It's going to be concave down. It's going to look like this. It's going to cross the x-axis here at this point. What is the coordinate at this point? Yeah. So we're going to add 1 to this. So we add 1 to this. It's going to be at negative 1/2, 0. I won't do the other one. So let's answer the question. The domain is x is greater than negative 3 over 2. In the range, I'm going to write it like this. And write. Okay, let's have a go at the exit ticket. This is 2.5 minutes for this question. Alright, let's have a look. So which of the following could describe a single logarithmic function? We can't be the first one because it goes to negative infinity twice. We can't do that. I'm looking at C, because we can't have a horizontal asymptote going towards 0. D looks good. Let me have a read through this one.
So K can't, like it doesn't have to.
Yeah, this one's a horizontal asymptote. Not at 0, but at some other value. This one is easy. It should be this one. Okay, we're finished with that lecture there for today. Take some time to work with your homeworks.